Bismillahirrahmanirrahim. Hello and welcome to the 13th video of this series. Today we will explore what are smart pointers, what is a concept of pointer in Rust programming language, as well as we will compare it with other programming languages, same as we did in our previous videos. So before moving forward, we just have a recap of our previous video. We covered how to publish the crate on crates.io, as well as we have developed a CL application with ClapCrate. So before moving forward with today's lecture, I just want to share a great resource with you all guys that I have found on the internet. This is a visual guide of a Rust type system, of the Rust type system. You will find all the code types and grades on this. So in this documentation or on this page, you will find the boxes where you can see all the types. Here you can see the trait, what are deref, and so on and so forth. You can find the types, right? If you want to explore or deep dive into each and every or explore, if you want to explore any of the type, you can click on the box. You will be redirected to the official Rust documentation. So here you can see I want to explore the I32, so it has redirected me to the official documentation. So, b- so now today's topic is pointer or smart pointers. So a pointer is a general concept for a variable that contains an address in memory. Pointer, what does it mean? It contains a variable, or it is a general concept for a variable that contains an address in memory. This is the simple concept we have already covered, that each and every variable contains an address in the memory. This address refers to or points to some other data. I'll explore it. I'll explain it to you. What does this mean? The most common kind of pointer is Rust. In Rust is a reference. Reference is kind of a pointer. What does this mean? Let me show you with an example. I have created a project with Cargo New, lecture 13. Let's just get a recap of this sentence. The most common kind of pointer is in Rust is a reference. So let's just create a reference. Let a is equals to let's say a string from, let's say, hello. And if I want to, here you can see I have created a variable with a string hello. Same, I have created another variable b with and assigned the a it to you, a it to it. So, and I have created another variable, let's see, and I have assigned the same variable a to the c. However, I am getting an error because you know what we have covered in our previous videos about the concept of ownership. I have moved the ownership of a to b, and now the ownership of a is diminished, you can say, and the actual ownership is being transferred to b. Now what if I want the value of a to have to be assigned to b as well as to c? So what I can do, I can pass the reference to the variable. Let's say I want to pass the I have added an ampersand sign. And what does this mean? I have passed the reference. You can see the type and string. Now, what does this mean? We have passed the reference of this A to B and C. This is pretty much clear for you. It's easy, simple concept because I have passed the reference. So what does this mean? A will point to, let me show you. I have created a variable in the memory. Let's just get an example. This is, let's say, memory A. Now I have created a variable b and c. So what does this mean? It will not create another separate block in the memory. What does this mean? It will point to a and then it will point to b. This is pretty much simple. What if I do this? B is equals to a. So what does this mean? The ownership will be transferred to b. So now a will be cancelled or removed and it will become b. or you can say we can create a separate, and you can consider B here. The same value will be transferred to B. Is it clear for you? Yeah. So let's move on to the next part. References are indicated by the ampersand symbol and borrow the value they point to, and this is pretty much simple. We have already reviewed that. Let's clear. Smart pointers, on the other hand, are data structures that act like a pointer but also have additional metadata and capabilities. Here you can see another point. Pointer has will point, let me show you. Pointer will point to the specific memory block. However, a smart pointer will have two separate things: metadata and other capabilities like length and other stuff. So now let's just get a quick recap of the concept of heap and stack. Let's just create what does stack means to you? Stack means pop and push. It's just the methods. They are the methods. These are the methods. So what does stack do? Stack is a will Stack will store the fixed size variables kind of thing. Let's say if I know, let's say I have created a variable. Let's just create let let a is let a is equals to, let's say the type will be I32 and is equals to, let's say, 5. So what does this mean? Sorry, what does this mean? The size of a will be fixed because of the type that is inferred to a. I32 will means plus minus 31 bytes. So what does this mean? 31 bits of the length, but the it will be stored in stack because it is a fixed size memory. Rust program knows that it is a fixed size memory. It will store it in stack. What if, uh, let's say I have created a variable. Let's say let name is equals to string from, let's say, Hadi. All right. So now what this mean, string will name is a variable which will be stored in stack. However, there is another thing. We have already covered this thing in our previous video. Let me show you. Let's quickly go to the uh, we have a lecture, uh, 8.2, storing UTF-8 encoded text with strings. So you can deep dive again or watch the previous video again, so to get a recap of this concept. So I'll just uh, make sure that you have understood this concept. String from Hadi header. It will The name variable will be stored in stack. However, there is one other thing. Let me do create a memory block here. This is kind of heap. Let's just consider it as heap. This is a heap memory. So now the name will be, because a string, the Rust program does not know what will be the length of the name string, or what will be the name, what will be the length of this variable name. So let's say I have created a in previous video, I have created a CLI application. In that application, I have asked from the user that pass the argument to input. But on the compilation time, when the program was compiling, the Rust program does not know that what will be the length of that specific argument. I have asked from the user input, and user can enter any of the length of, let's say, user can type in a proper sentence, user can pass a specific character or whatnot. So this means that the this data will be stored in heap. So a heap will is not be considered as a fixed size memory. You can enter any number of length of variable, the string or integers, whatnot. It will be stored in heap. However, the metadata or basic details of this variable, let's say this is stored in heap, However, the metadata, let's say length will be stored. Let's say what will be the length of this string. Let's say it has length of 10. Just an example, metadata would be metadata, and there are multiple other uh, capabilities that the pointer contains. This block will contain. Now, this will be called as a pointer because it will point to this specific memory block. क्या मतलब है इसका कि अगर मैंने कोई भी लेट्स से मैंने कोई एक वेरिएबल बनाया और उसकी फिक्स साइज लेंथ नहीं है, अगर फिक्स साइज लेंथ होती तो वो तो सीधा सीधा स्टैक में चले जाता। हाउएवर इसकी फिक्स साइज लेंथ नहीं है तो वो चले गया हीप में। रस्ट प्रोग्रामिंग ने इसको हीप में डाला और जो स्टैक में उसका पॉइंटर रखा। क्या मतलब उसके पास मेटाडेटा और अदर कैपेबिलिटीज होंगी, लेंथ हो गया और इस तरह की डिफरेंट डेटा होगा जो कि स्टैक में होगा, और वो जो डेटा होगा वो पॉइंट कर रहा होगा उस मेमोरी ब्लॉक में जहां पे वो डेटा असल में स्टोर्ड है। स्टैक में डेटा, द डेटा इज नॉट स्टोर्ड इन स्टैक, इट इज द डेटा इज स्टोर्ड इन हीप। द मेटाडेटा एंड अदर कैपेबिलिटीज आर और लेंथ वगैरह are stored in stack. So this is pretty much clear. Let's just get at this example. So stack memory, there is a pointer S2 pointer that points to the heap memory hello. This is pretty much simple for you. So if you have any confusions, just let me know. So let's just move on to the next thing. Rust, with its concept of ownership and borrowing, has an additional difference between references and a smart pointers. While references only borrow data, reference will only borrow data. In many cases, smart pointers owns the data they point to. Though we didn't call them as such at the time, we have already encountered a few smart pointers in this book, including string and vector T, the generic and the vector. So we have only covered the string and the vector type. So let's just move on to the next thing right here. All right, smart pointers are usually implemented using structs. Unlike an ordinary struct, smart pointers implement the deref and drop traits. We will explore what are deref and drop. This allow the deref traits allow trait allows an instance of the smart pointer struct to behave like a reference, so you can write your code to work with either references or smart pointers. The drop trait allows you to customize the code that runs when an instance of the smart pointer goes out of scope. So let's say if any of the instances goes out of stock, so the drop trait comes into the place. What do you mean? That it will allow you to customize that specific instance of a pointer. So let's just quickly, these are the methods, or these are the pointers that we will cover. Let's say box, RC reference counting pointer, the ref cell, ref mute. So let's just move on to the uh, pointers thing. The first pointer using box T to point to data on the heap 15.1. So this was the pretty much theory in the 15th chapter. We have 15.1, the subchapter of the smart pointers. What is box? Let's just quickly go and get an example of it. Let's say I have a variable, let's say num, and I have the value 5. The default type is i32. It's fine. What if it will be stored in stack because the length is fixed, the size is fixed. It will be stored in stack. What if I want to store it in uh, heap memory? So how can I do this? I can do this by num is equals to box new, and let's just this as a pointer that will store this variable or this value to the heap memory. So now let's just go to the documentation. The most straightforward smart pointer is a box whose type is written box T. Boxes allow you to store data on the heap rather than the stack. We have already implemented this concept. This is the basic concept. However, let's just go on to the deep or the complex example of this. Let's consider an example. Let's say I want to build a linked list. Linked list means, um, let's say a data, or we have a head and the tail. The head and the current memory blocks. Let's say head, the current item or current value, and the tail. Or let's just consider, or let's take an easy example, the current one and then the next value. Current will have, let's say, current value, and this next means next. This will point to the next value. Let's say I have another 4 and I want to do a recursive call. What does this will do? I want to do a recursive calls. Let's say I have a let's say I have a struct or enum. I have a struct. Let's consider I have a struct, and inside that struct we have a, let's say, let's consider an example, do an hands-on implementation of that. Let's get into the code. Let's say मैं एक enum बना लेता हूँ यहाँ पर shape. We are already covering the same example from the video one, the shapes example. So let's say we have, let's say, shape kind. Let's just do that shape kind, and we have, let's say, square, triangle, rectangle. All right, let's just go to the uh, enum, and we can consider, let's say, build shape, and inside that shape we can create a default shape. Let's say what can be multiple enums can be here. Let's say we have node. Node means this node. This is a node. Let's consider it as a node. And inside that node, we have the value and the this next. So let's say we have a node and we have a current value. Let's consider it as a string. Oh, sorry, a string. And inside in the next, we ask the Rust program to do shape and nil. If there is no shape, then it can be considered as nil. Now here you can see an error. Recursive type shape has infinite size. What does this mean? Rust program does not know what will be the size of this shape, because I'm doing a recursive call. Let's say I want to call this multiple times. This next function will call another, this next function will call another, and let's say at the end it will refer to or points to this. So it can become a circular or life cycle of these linked lists. So it can be become a circular loop or infinite calls. So to avoid that, what we have, we can go into that, and let's create box new. Sorry, box, and add a shape. Now the error is gone. Let's create a variable. Let shape let shape one is equals to, let's say, node. The node, first node, will have, let's say, string of name from node one. Or let's, instead of okay, let's just do one thing. Assign the shape kind, and here, instead of providing string from, let's provide square, pass the square, and let's pass the next node to it. Let me pass the node. However, we have, let me do with this same stuff. Node, and let's say it will be triangle. And I don't want to pass another node. I want to make it nil. However, there is an issue. Okay, shape kind, as well as there is. Let's just pass the shape to this. All right. So now we have an error here. Arguments to this enum variant are incorrect. Store this in the heap by calling box new. I'll store by using box new, I will store this node inside heap. So let's say box new, and let's just pass this shape kind, and here box new nil. Perfect. We have created a shape one, and if I want to print it, let's print, and let's say shape one, print it, save it, and okay, I haven't implemented right the debug macro. Derive debug. अगर यहाँ पे कोई issue है, if you have any queries, just let me know because it is a complex concept. So shape kind doesn't implement debug. So let's just implement the debug trait, debug macro, sorry, and let's just save it. Cargo new or cargo run. Here you can see node square. First node has the name square or the shape name is square. The second node has the name triangle nil and then nil. What does this mean? We have, let's say we have a name here. Let's say square. Now the second one, it is pointing to the next function. What does this mean? Let's just create another function. Store the angle. The name of the shape is triangle, and it has, you can uh, do another thing. You can point to another shape. However, I haven't passed or I haven't pointed the next one to any shape, so I made this null. So the tail is, there is nothing, it is not pointing to any of the thing, it's null. Or you can also do one thing, you can pass empty here. If you want, you can pass the empty here. You have multiple choices you can opt for. Let's just go back to the documentation. So now when you have a type whose size can't be known at compile time, and you want to use a value of that type in a context that requires an exact size, when you have a large amount of data and you want to transfer ownership, but ensure but ensure the data won't be copied when you do so. When you want to own a value and you care only that it's type that implements a particular trait rather than being of a specific type. Boxes don't have a performance overhead other than storing their data on the heap instead of on the stack, but they don't have many extra capabilities either. You will use them most often in these situations. These situations we have already discussed. Now let's say, all right, they are uh, showing you the example right here. We have already we have already covered the hands-on implementation, enabling recursive types with boxes. So now they are implementing the recursive call. They have created a cons or node, both are similar implementation. Cons usually implemented in functional programming like Lisp or any other Alex or any other programming language, or however node used to be implemented or usually implemented on the OOP, object oriented programming language. So there is not major difference between them. So let's say they have created a linked list I32. They are storing I32 and the recursive call to this list. So they are showing the error, that uh, why there is an error. So they are showing the error by running the cargo run command. Now here they are showing with another example. So now here you can see they have implemented a box and so on and so forth. So this is pretty much it. So uh, let's just run this shape. Let's say I want to print uh, the this all the shapes in that specific. Let's say I just want to print the names of these, let's say, nodes or the shapes. What I can do, there are multiple implementation. Let's just opt for this easy implementation. Function print shape name, and let's say node. I will receive node as a function parameter, and let's just uh, assign it the type, the reference of the shape. We will not be returning anything because we want to have a recursive call to print the name. So let's say match the node. So node will have two things. Node will have this node will refer to the shape enum, and then the shape enum has two things, node or nil. So node will have, let's say, let me show you. Node will have, let's say, shape, or yeah, shape, and then the second variable would be next. Inside that, I want to do one thing. Let's just print the name of the shape. Let's say shape and then shape. Here you can see. Okay. And then let's say what I want to do, I will call this function recursively. So recursive means a function will call itself again. So let's say call this function and pass the next node to it. Next, and pass, we don't have to pass the reference because the next is already a reference of shape. Here you can see the shape. And then the other will be nil. So nil will, let's say, let's just print nil, and shapes ended, let's say, and let's just use this. Okay, node cannot find tuple struct or tuple variant node in this scope, not found in this. Consider importing this tuple, use create shape node. Let's just do one thing, and then let's say pass the shape one as reference. Pass the reference to shape one, save it, and do one more thing. Shape colon colon, and this shape doesn't implement display. All right, and this shape. Let's just do a cargo run. We have shape square, triangle, and then we have a print shape ended, and we have, let's just comment this out. Here you can see the names of all the shapes, square, triangle, and the last one, the print is here, shape ended. There are multiple implementation. You can uh, run a loop here and add the match statement, and there are multiple implementations you can go for. So let's just move on to the next chapter. So I hope this is clear for you. So let's say, okay, so now treating smart pointers like regular references with deref. Deref is a trait. So implementing the deref trait allows you to customize the behavior of the dereference operator, not to be confused with the multiplication or glob operator. By implementing deref in such a way that a smart pointer can be treated like a regular reference, you can write code that operates on references and use that code with smart pointers too. So we can implement this example. Let's say, let me show you an example right here how they are implementing the deref trait. Here you can see the deref trait will look like this. So implementation of the generic deref for my box. They have created a my box struct which will accept the this. Let me which will accept this generic, and then they are doing this stuff. So what this will do? This will help you. It will. Let me show you an example. Let's come here. What we usually did in our previous examples, let's say, let's consider this. Let's take another reference here. The node will take the reference of this node to match for matching this function. Let's say if I want to pass this, I'm passing there is a reference to this next, and I'm passing the reference to this next again and again. So let's just go and let's just implement one. Let's say in our previous examples or in our previous videos, what we used to do, let's say like A is equals to, let's say, shape 1. Now let B is equals to shape 2, sorry, shape 1. Let C is equals to ampersand B. Here you can see um, borrowed move value. Where are we borrowing? All right, okay. So let's just remove this. Let's just get a reference of it and A, pass A here. Now here you can see the first type is here A, and we have passed the reference of shape 1. So the type is ampersand shape. Now here what I am doing, I am passing the reference of shape 1 to A and passing the reference of A to C. The type is becoming double ampersand shape. So let's say let B is equals to ampersand or ampersand shape. Or let's just, so what in our previous concepts, what we used to do, we used to, let's say, C is equals to, let's say, or plus equals to 1. With, let's say, if we are working on with integers, what we used to do, we used to dereference this C and we are adding or incrementing by 2. क्या कर रहे थे हम, जब हम इंटीजर्स के साथ वर्क कर रहे थे तो क्या करते थे हम, एक एस्टेरिस्क लगा देते, तो व्हाट इज दिस एस्टेरिस्क डू, इट dereference it from this, that's this mean. So now if I place the multiply C is equals to, let's say, 1. This is just an example, it's not a correct syntax. So let's say C is equals to 1. So what it will become, let's say C, the type will become shape is equals to ampersand A. Sorry, the type will become C colon ampersand shape, यानी एक बार reference रह जाएगा. And what if I place 2 multiplicative? So it is dereferencing twice. So what does this mean? Now there will be no any reference remaining. It will directly get the ownership of that specific shape. So I hope this is clear for you. So here you can, let's say, without deref, what you have to do, my box new string from Rust, and then you have to implement the ampersand, take the reference, dereference it, and the other functionalities. So how deref quotient interacts with mutability, similar to how you use the deref trait to override the multiplication operator. What does this mean? The dereferencing. On immutable references, you can use the deref mut trait to override the this multiplication operator, the dereferencing operator. So now you can directly work with this. It's pretty much easy for you because the Rust, we can call the hello function with a ref string slice as an argument, such as hello Rust. For example, deref cohesion makes it possible to call hello with a reference to a value of type mybox string as shown in listing. So they have implemented the deref cohesion and then it's working perfectly fine. So this is pretty much it. Let's move to the next concept of drop trait. It helps you to um, customize the specific pointer if it is out gets out of scope. So the second trait important to the smart pointer pattern is drop, which lets you customize what happens when a value is about to go out of scope. You can provide an implementation for the drop trait on any type and can be and that code can be used to release resources like files or network connections. We are introducing drop in the context of smart pointers because of the functionality of the drop trait is almost always used when implementing a smart pointer and not what so. So they are implementing a drop trait for customize. They have created a struct and they are implementing the drop trait. So what does this helps them? So let me show you. So what does this mean? Let's just quickly update this enum and replace it with, or just remove this or comment this out and implement struct. Let's say struct. All right, let's create a struct, and let's say shape. Um, we have, let's say, the name of the shape. Let's say name will be shape kind, and then it will point to the next. There will be a next field which will be of type shape. Now there is an error. What does this mean? Because I want to make it optional. There is another thing. Let's just add the box. However, there is another thing because I want there might not be always the shape will be present. Might be there will be possibility that there is no shape present. It will not. It is not pointing to any shape. So what will we will do? Let's just implement an option trait. So what does this mean? If there is any, if it is pointing to any of the shape, it's fine. It we will get this from sum. However, if there is none, so we can, let's say the next will be none, next will be none, or either will be sum. In here we will get the shape. So let's say, okay, we are, let's just comment all this stuff. Okay, let's go to the next implementation. So let's say let shape 2 is equals to, let's say, because we are working with this struct, so how we can implement the structs with this thing. So let's say we have shape, and inside that shape we have name and the next. So let's say name will be shape kind. Let's say triangle is the first shape, and then the next field is next, and we have multiple options. Let's say sum, the sum will have a box. So let's say box new, and it will refer to another type. Let's say add other shape, and inside that shape, let's say shape kind rectangle, and then next, and we are not passing anything to this shape, so let's consider it as none. All right. Okay, now let's say I want to print it, print ln, and then video is working fine. Yeah, all right. So shape in issue, what's happening? Shape 2. Let's just print this out, run the cargo run command, cargo run. Here you can see we have shape. Inside this struct, we have a name triangle. Next, there is a some shape which is rectangle, and then there is nothing in this next. So we have only two shapes. So we can run the print command. We can update the print function later on. Let's just move to the documentation, back to the documentation. Now here they are implementing the drop trait. However, they are explaining that when the when this custom smart pointer will gets out of scope. So let's say C, D, and then they have printed custom pointers created. So custom pointer created, dropping, and then dropping with V. So what does this mean? So when you are dropping any of the uh, let's say let me show you an example. So what does, let's just remove everything. So when the Rust program runs, it will drop each and everything in, let's say, from bottom to up. So it will work like this. Custom pointers created, it will print first, then other stuff, then my stuff, and then the print stuff. So custom pointer created, other stuff, and then my stuff. So I think it's pretty much clear for you whenever you okay, there is another thing. Let's say I want to drop this. So Let's run the function drop. Inside that drop, let's just pass the shape to. Here you can see I have an error. Borrow of moved value shape to. Here I have passed the. Now what it means, calls to the STD memory drop with a reference instead of an owned value does nothing on by default. It will do nothing because I have passed the reference. What if I, let me just remove this and let's say cargo run. Here you can see it is and save cargo run. Nothing is printed and nothing is has happened yet because I have dropped this and I cannot. And if I pass the reference to it, so it won't do anything. Cargo run. So shape is printed simply as it was working previously. However, let's say the C dot not works because there is another concept, destructor. Explicit destructor calls not allowed. We have to use like this. We have already covered that how we can use that. Custom pointer created, custom pointer dropped before the end of main. After the main function, everything gets dropped out of scope. However, if I want to drop beforehand, before ending the any specific function or any functionality, we can use this drop function imported from the STD, the standard library, memory, and then drop. So this is pretty much clear for you. Let's just move on to the next smart pointer. So we are getting deep and deep dive into the complex concepts of the Rust programming language. So I'm trying to explain it in as much as clear for you as possible because मैं जितना अपने तरीके से समझाने की कोशिश कर सकता हूँ, अपनी तरफ से जो एग्जांपल इम्प्लीमेंट कर सकता हूँ वो मैं करने की कोशिश करता हूँ. सो आई होप आपको ये समझ आ रहा होगा. अगर कोई भी चीज़ ऐसी हो जो समझ ना आ रही हो, so you can reach out to me on comments and in comments and I'll uh, answer you or answer your queries. So let's say मैं आगे बढ़ जाता हूँ. So what we have in the RCT. So RC, reference counted smart pointer. So in this, in the majority of cases, ownership is clear. You know exactly which pointer owns a given value. Yes, we do know beforehand when we are declaring any variable, defining any variable. However, there are cases when a single value might have multiple owners. Let's take an example. What does this line mean? Let me show you. Multiple owners. Let's say, yeah, let's just consider this example. This is referring to this. Let's say I have a shape, let's say rectangle. Let me create another thing. Let's say rectangle, which is pointing to this. Then I have another, let's say, let's create another thing. There is any other shape, let's say, let's say triangle, and then it is also pointing to this square or this shape or structure. So now you mean now it is clear for you that multiple owners means that this in this place the it will point to this and there will be it will point to this. There are multiple owners of the multiple stuff. For example, in a graph data structure, multiple edges might point to the same node. In the graph, let's say, so there are one node, let's say, and in this node we have, let's say, two nodes, and let's say there is only one node, there is multiple nodes, let's say. So this is how, what does they mean? So that node is conceptually owned by all of the edges point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it and so has no owners. So let's move on to the actual implementation using RC reference counted pointer to share data. So they are, I have already told you what does they mean. So let's say, let's just implement or replace this implementation of box pointer with a reference counted pointer. But because we need, mm, let me show you what I mean. Let me comment it or everything out and uncomment this. Comment this out really quick. Save it. ठीक है, यहाँ पर आ जाते हैं मैं. Let's say shape one. Copy this here, and copy and paste it here. Let's say shape one has node and use shape as basic. Let's just move it to top. So if I can. Alright. यहाँ पर मैंने क्या किया कि मैंने एक node बना ली और if I want I can pass this into a box. Right. Okay. So let's say मेरे पास एक shape है. I have a shape and let's point this shape to another variable. Let's say I have another shape 2 and let's just point shape 1 to it. Shape 1 and let shape 3 is equals to shape 1 because both of these shape, let's go to the escalator. Both of these, both of these is pointing to this square. So what does this mean? They want to be owner of this shape 1. So how this can be possible? So this can be possible by implementing the RC, the reference counted pointer. So let's say here instead of box, let's just replace it with RC and let's just come here and let's just replace our box with RC and here, right here, you can import from the std lib. All right. So let's say if I want to create a new reference counter pointer, so what I can do, I can do rc and clone it. I cannot directly clone this. Let me show you an example. If I want to clone shape one directly, I don't have any method right here. And if I want to do shape one dot clone here, so now what it is doing, it is cloning the reference counted of shape. Let's say if I revert back this implementation and try to implement this same cloning thing with box, save it, and here you can see an error. The method clone exists for struct box shape, but its trait bounds were not satisfied the following trait. I have to implement the clone. Doesn't satisfy shape clone. We have to implement the clone by ourselves. Thus doesn't support by default. So let's just revert back to the Rust new. We can directly do shape one dot clone, or rather we can do, let's say, shape one. Let's say, all right, here you can see, consider borrowing here. I have to add the borrow here, save it. Why it's taking too long? Everything is working fine. Another thing, mismatched. All right, perfect. So now the I can clone both all of these shapes. So the expected what we were expecting or what we were expecting that we have to point or there must be multiple owners of a single shape. So let's say I want to print let's say shape T, shape shape 3. Let's just save it and print it. Now I have same thing as I have in shape 1. However, what if I want to get the count? How many times does this shape one is being how many times does we have cloned, or we got the reference of that specific shape? So how we can do that? Let's just we have a method. Let's say count, yeah, RC count, reference counting out RC. Let's say, and let's just do one thing. We have RC colon colon, and we have a method strong, and inside that we have to pass the shape one, and that is pretty much it. Here you can see gets the number of strong RC pointers to this allocation, and let's just pass the save it cargo run RC3. Let's just what does this mean? First time shape one has the reference counter, yeah, or the pointer one, the value of the pointer two, the pointer will be two, and then shape at the on the shape three it will become three. So if I want, let's just move to one, two, you can see, and you will see one, two, and three. Is it clear for you? I think it is. So I hope it should be clear for you. Cloning and RC reference counting increases the reference count. They are already implemented, and that's enough. That's pretty much it from this thing. Let's just move on to the next topic, RefCell. So let me get some water. All right, let's continue with the documentation, chapter 15.5, RefCell. What does this RefCell means? RefCell and the interior mutability pattern. So interior mutability is a design pattern in Rust that allows you to mutate, sorry, control shift X, shift hash, mutate data even when there are immutable references to that. Normally, this action is disallowed by borrowing rules. What does this mean? Rust allow you to mutate data even there are immutable references. Let's say, what does this mean? Let me go back to the code. Let's comment everything. Or let's just let A is equals to 3, and then let B is equals to, let's say, 3. Oh, let's just do one thing. Let A is equals to 4, 5. Now Rust is throwing an error. You cannot mutate immutable variable. You cannot mutate an immutable variable. You have to pass, let's say, mute keyword, and then you can mutate it. However, what RefCell do, RefCell help you to mutate data even if it is immutable. So how we can do that? We have a function borrow mute. So let's say normally this action is disallowed by the borrowing rules. To mutate data pattern uses unsafe code inside a data structure to bend Rust's usual rules. Okay, one more thing. In starting or when we have started learning about Rust, हम जब Rust पढ़ रहे थे हमने सीखा था कि Rust is a type safe language. However, now here you can see the pattern uses unsafe code. So this means you have choices. Rust is by default type safe. The safe you can the beside that the default implementation of the Rust is safe. However, if you want to do unsafe implementation, you can do that. Rust allows you to do that by creating a separate isolated block, by defining the ref cells, and so on and so forth. Unsafe code indicates to the compiler that we are checking the rules manually instead of relying on the compiler to check them for us. We will discuss unsafe code more in chapter 20. So now enforcing borrowing rules at runtime with RefCell. How we can implement the borrowing rules at runtime with RefCell? अगर हम अपनी पुरानी ही इम्प्लीमेंटेशन पे सेम काम करना चाहें, what if I want to implement the same thing on this? So I won't be able to do that directly. I have to update something. I have to implement another pointer RefCell. So let's say RefCell. Okay. So cannot find RefCell, and I have to import the RefCell from the standard library, and it's perfectly fine. Now we have an error here. So instead of RC new, we have to add another syntax or another code block. So let's say ref cell new, same as we used to do. Let's say we have here ref cell new, and then paste it here, and then ref cell. All right. So now, what if I try to print the shape one where it is? Let's comment this out. Comment this. Okay. Uncomment shape one, shape one, and then run the command. Go run. All right. So we have run the command ref cell value is node square ref cell. So what does this mean? Ref cell has a value field in that. Then another node ref cell has a value, and then in that value we have a node triangle ref cell has a value, and then it is nil. The value is nil. Let's get back to the documentation. So here, because some analysis, let me go back. The advantage of checking the borrowing rules at runtime instead is that certain memory safe scenarios are then allowed where they would have been disallowed by the compile time checks. Static analysis like the Rust compiler is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the. So Rust cannot, uh, let's say, Rust cannot identify the race case or the race case in the on the compile time. So what does this mean? Race case क्या मतलब कि let's say कि एक ही रिसोर्स को let's say this is R1 resource 1, एक रिसोर्स को दो प्रोसेस लेने जा रहे हो. लेट्स से एक प्रोसेस P1 है एंड एक प्रोसेस P2 है. सेम टाइम पे दोनों प्रोसेसेस एक ही रिसोर्स को गेट करना चाह रहे हो. सो नाउ द रेस और डेडलॉक विल कम इनटू प्लेस कि भाई यहाँ पे डेडलॉक हो जाएगा. दो रेस कंडीशन है ना कि P1 और P2 दोनों एक ही रिसोर्स को लेना चाहते हैं. व्हाट इफ लेट्स टेक एन एग्जांपल. Let's say I have opened a OBS studio to record my video or this stuff. So let's say OBS is trying to get any specific, or let's consider VS Code. VS Code is trying to get this lecture 13 folder to be opened, or it is trying to save the data. Let's say I have made changes. Let's say VS Code is trying to try to save it or try to access any of the resource from the PC. Let's say VS Code चाहता है कि मैं कोई फाइल ओपन करूं और सेम ही टाइम पे एक और कोई प्रोसेस आता है और उसको भी वही काम करना होता है. सो नाउ यहाँ पर एक रेस कंडीशन क्रिएट होगी. वी हैव मल्टीपल इम्प्लीमेंटेशंस और सॉल्यूशंस टू अवॉइड दीज रेस कंडीशंस एंड द डेडलॉक्स. बट व्हाट वी हैव what what this documentation means that Rust cannot identify the halting problem, which is beyond the scope of this book, but is an interesting topic to research. So we will also cover all these implementations later on because some analysis is impossible if the Rust compiler can't be sure to show the code compiles with the ownership rules. It might reject a correct program. We are already on 59 minutes mark. So in this way, it's conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, If Rust rejects a correct program, the programmer will be convenienced first, but nothing catastrophic can occur. The RefCell type is useful when you are sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. So let's say delete all this stuff. Similar to RefCell is only for using in single-threaded scenarios and will give you a compile time error if you tried using it in multi-threaded context. All right. Here is a recap of the reasons to choose Box, RC, or RefCell. So they are giving the recap. So why we have to use this? So let's say enables multiple owners RC at the same time, allows immutable or mutable borrow checked at compile time, and then allows the ref cell allows mutable borrows checked at runtime. You can mutate the value inside the ref cell even when the ref cell is immutable. It allows you to allows mutable borrows checked and at the runtime, not at the compile time. So let's say, so now they are implementing this stuff. Let x is equals to 5, y is equals to. They are trying to instead of passing mute here. Oh, instead of passing mute here, like text, let mute is equals to let mute a is equals to 5. Instead of doing this, they are doing let a is equals to 5. So and let b is equals to, they are doing this, taking the reference, and so Rust will throw an error because by default this a is immutable. If I want to mutate this, I have to pass the mute keyword here. So now what they are doing here to avoid this condition, to avoid this error, here you can see. So they are going to the complex concept. So let's just get back to our older example um, right here. So we have already implemented the ref cell here. So now let's just comment all this stuff. Now what I mean, I want to borrow mute, or I want to mutate this shape one. How we can do that? Let's just get back to the example, or just think about that. So let me do one thing. Shape one dot. Let's see what we have. We have borrow mute, get mute. So what does this borrow mute do? Let me just, what does this borrow mute have? Public function borrow mute, it gets the self and return this reference to the mutable. Mutably borrows the wrapped value. So what, let's say, let shape 2 is equals to shape dot. Right here, ref mute. It is, the type is now ref mute shape. And if I want to print this, where it is, shape 2, let's just print it out, cargo run. What we have, shape 2, it's the same example. We have it, node, square, ref cell. At the first place, we don't have any ref cell and value, but it's mostly the same implementation. Now, how I can mutate it? So let's get an example for that. So let's say what I can do. Let's create a function to print it, or let's just, all right, let's just do one thing. Instead of creating a separate function, let's just implement a loop. So we we can see कि हमारे पास दो different examples की तरह different examples से हम print कर लेते हैं, ऐसा कर लेते हैं. So let's say loop, let's just do one thing. Let the current pointer will be, let's say, the shape, take the reference of shape 1, and let's say loop. Let's run the loop again and again, and let's say match. But okay, let's just do one thing. Let's current and then match. Now here what if I want to get the node out of here? How we can, because Let me show you. We had a shape node. Let's just copy this example instead of okay. Let's just save it. All right. Here you can see an error. Node. Let's just remove this. Let's just remove this. Let's just remove this. And here, यहाँ पर हमारे पास एरर आ रहा है. Expected struct RC ref cell shape found enum shape. Now, another thing, it's there are multiple issues in that example. So how we can resolve these issues? कि हम अपनी this इस example से issues को किस तरह resolve कर सकते हैं? So what I can do, I can take I can borrow the current. So how I can do that? Let's say current is equals to mm, all right. Let's say shape one dot borrow, and let's say current, or you can say, or let's say borrow. Let borrow is equals to, we have borrowed it. Now the type difference, you can see the type difference, reference counted pointer is removed. In this type you have reference to that specific shape. What if I want to dereference to that? So let's say derefer borrow. Oh, now what we have in this type, let's save it. What we have, where we have an error. Match expression, and then okay, node. Okay, we haven't implemented the, okay. So now यहाँ पर हम देखते हैं अब what we did, we have borrowed the shape one. हमने borrow किया, तो यहाँ से reference जो RC था वो चला गया. So let's say if I want to take the shape current, यहाँ से करंट का मैंने अगर बोरो ले लिया है तो भी मसला नहीं है. करंट मेरे पास रेफरेंस आ गया शेप का. अब मैं यहाँ पर डी रेफरेंस करूँ. अगर मैं यहाँ पे डी रेफर ना करूँ ना, तो मेरे पास क्या है, हियर यू कैन सी दिस एक्सप्रेशन हैज टाइप रेफरेंस टू दिस शेप. हमारे पास रेफरेंस है. सो टू डी रेफर दिस वी हैव टू इम्प्लीमेंट दी डी रेफ. Let me show you the in the documentation. Let's go back to the where is deref? Yeah, right here. So what this deref does? Deref, here is the trade. Where is the trade? Where is the trade? Yeah, right here. What this deref does? Deref allows you to, it trait allows you to customize the behavior of dereference operator. सो डी रेफरेंस का मतलब है कि भाई मैं वी आर डी रेफरेंसिंग टू, लेट्स से एनी स्पेसिफिक थिंग, वी आर डी रेफरेंसिंग फ्रॉम दिस करंट रेफ. नाउ हमारी करंट इम्प्लीमेंटेशन, लेट्स से अगर मैं कार्गो रन करता हूँ, बट बिफोर हैंड लेट्स जस्ट ऐड अ ब्रेक व्हेन इट इज देयर इज नील ब्रेक. ओके, वन मोर थिंग, we just don't want to run this loop again and again or infinitely. Instead we will do current is equals to next. And now यहाँ पर एक और चीज, cannot mutate immutable variable current. I cannot mutate, so let's just add a mute here, save it. Here you can see borrow. Borrow does not live long enough. Borrowed value does not live long enough. Binding borrow declared here. Borrow later used here. So what I have to do? I have to implement the lifetimes. So there are multiple implementations that we go for. So we can let's say implement the lifetimes here. We can implement the borrow mute here. So let's just think about that. What we can do. सो यहाँ पर हमारे पास एरर ये है कि कंसिडर यूजिंग क्लोन हेयर. सो व्हाट इफ आई, बाय सजेशन, अगर मैं यहाँ पे क्लोन यूज करता हूँ, एक और चीज, So now we have current cannot assign to current because it is borrowed. Borrow might be used here when borrow is dropped. Wait, where are we dropping? Oh, all right. So here we are using shape one borrowed mute. So let's just comment all these as stuff and then let's just save it. Now here you can see cannot assign to a current because it is borrowed. So what does this mean? Because we are borrowing current dot borrow. We are borrowing here and dereferencing to it. So let's say what we can do, we can implement, let's say, um, instead of before dropping this borrow, what we can do, let's just save it into inside a variable. Let's say next counting, next RC, let's say next reference counting pointer. So let's say if I want to do clone of it, let's RC clone, and then let's say pass the next to it. And instead here next RC, we can still see the same issue, but let's just use the drop and drop this borrow before this closing bracket. So we are dropping this borrow beforehand. We are not dropping this borrow right here. We are dropping the borrow right here before the reassigning to current. So let me just run this code cargo run, and now we can see the successful thing: shape square triangle, sorry, shape square triangle and ended. What we had square and triangle, and after that we have nil. So because to avoid the nil, we have already printed the shapes ended break. So I hope, because this is a complex concept, so यहाँ पर अगर मैं repeat कर दूं, borrow, हम borrow कर रहे हैं करंट को टू रिमूव द रेफ सेल। ये जो है ना रेफ सेल, यहाँ से रेफ सेल और रेफरेंस काउंटिंग पॉइंटर को रिमूव करके अब हमारी टाइप क्या बन गई? द टाइप इज बिकमिंग रेफ एंड इट्स द रेफरेंस ऑफ द स्पेसिफिक शेप। हम यहाँ पर डी रेफरेंस कर रहे हैं और इसका यानी रेफरेंस तो ले रहे हैं लेकिन बोरो को डी रेफरेंस कर रहे हैं। So now we are printing it before we are using the drop function to drop it, and then the current RC we are printing it. So let's just get back to the documentation. Here we have, let's go to the 15.6 reference cycles can leak memory. So let's say, okay, beforehand, I just got one concept to explain you. So in previous topic about DREF, so I thought why not explain you how DREF works. So let's say let a is equals to, let's say हमारे पास एक string है, string from Hadi. Let b is equals to, let's say box, let's say 5 हमारे पास. Let c is equals to, let's say मैं b assign कर दिया. Now the type is box I32. हमारे पास जो इसकी type है वो क्या है? I32. Let's say d is equals to, or let's just do one thing. Let's just assign the reference, pass the reference of that specific smart pointer. What if I want to remove the reference of that specific smart pointer? So I can do that by removing this. Now here you can see the reference is being removed but has type I32, which does not implement the copy trait. So now you have to implement the copy trait to replicate this topic or this concept. Now this is, I hope, pretty much clear for you to derefer. What if I want to remove the smart pointer? So I can do that. If I want to remove, let's say मेरे पास यहाँ पे इस what's the type of this C? It's the smart pointer of I32. It is stored in heap. But what if I want to remove the smart pointer? I want to store it in stack. How I can do that? I can implement the dereference and it will be stored inside the D variable. So I hope ये भी कॉन्सेप्ट क्लियर होगा. लेट्स से मैं यहाँ पे कमेंट्स ऐड करते चले जाऊँ ताकि आपको क्लियर हो जाए. लेट्स जस्ट ऐड कमेंट, रेफसेल Um, oh, there are a lot of stuff right here. Let's just move back to the top. Okay, so we have written a lot of code in today's video. Let's just uh, read this theoretical topic. So in reference cycle, this can leak memory. Thus, memory safety. Let me just quickly add it. Okay. Memory safety guarantees make it difficult but not impossible to accidentally create memory but that is never cleaned up, known as memory leak. Let's say कोई भी memory है जो कि clean up नहीं हुई, possible है. Preventing memory leaks entirely is not one of Rust's guarantee. Memory, meaning memory leaks are memory safe in Rust. Memory leaks considered as memory save in Rust. We can see that Rust allows memory leaks, but by using RC reference counting and RefCell, it's possible to create references where items refer to each other in a cycle. एक लिंक लिस्ट एक का हेड सॉरी एक का टेल दूसरी हेड को रेफर कर रहा है एंड देन द टेल इज रेफरिंग टू एंड देन लेट्स से the last one is referring or the last tail is pointing to the first one's head, the head of the first linked list, the element. This creates memory leaks because the reference count of each item in the cycle will never reach zero and the values will never be dropped. So they are implementing, let's say they are implementing the linked list, the tail has a self, let's say, and then they are implementing this stuff and then they are creating rc new the cons young means linked list refcell new and they are creating so initial rc count rc strong they are printing the count a dot tail is a function inside the implementation of the list. They are implementing the or printing the reference count, b initial reference count, b next, and then inside let's say a initial rc count is 1, some ref cell next item is nil, rc count after b creation 2 हो गया, b का initial reference count 1 था, b का initial 1 था, b's initial reference count was 1. However, the a's reference count, the variable a's reference count is 2. बी नेक्स्ट आइटम बी का नेक्स्ट आइटम ये है जिसका फिर अगर इसका हम इसका रेफरेंस काउंट लेंगे तो 1 इसका 2 और इस तरह बी रेफरेंस आफ्टर चेंजिंग ए इज इक्वल्स टू 2 आफ्टर चेंजिंग ए इज इक्वल्स टू 2 and then they are explaining like this b is pointing this 10 is pointing 5 so you can see the circular this is the life cycle 5 and then it is this is a circular path so it is referring this and it is also referring to this. So preventing reference life cycles or reference cycles using VT, so far we have demonstrated that calling RC clone increases the count, strong count of an RC instance, and RC instance is only cleaned up if its strong count is 0. So let's say reference counting इंस्टेंस पॉइंटर का इंस्टेंस उस वक्त खत्म होगा जब the value of a strong count is becomes 0. So let's say you can also create a weak reference to the value within RC instance by calling RC downgrade. आप ऐसा भी कर सकते हैं, you can call the RC downgrade and you can pass the reference to the reference count and then it will become the weak reference. So let's say यहाँ पर example आ गए node, they are implementing the node right here, creating a tree data structure, a node with child nodes. To start with, we will build a tree with nodes that know about their child nodes. We will create a struct named node that holds its own i32 value as well as references to its children node values. It's pretty much clear for you. So एक struct बना लिया, same as we did. They have created this. Now the major concept is here. They have created parent and their children inside that node. अब मैं यहाँ पे आ जाता हूँ विजुअलाइजेशन पे. विजुअलाइजिंग चेंजेस टू स्ट्रॉन्ग काउंट एंड वीक काउंट. एक लीफ बना लिया यहाँ पर, फिर उसने प्रिंट किया वीक और स्ट्रॉन्ग काउंट को. स्ट्रॉन्ग काउंट एंड देन लीफ काउंट. गो बैक टू द printed. Where is this? They haven't shown you the print. So let me just copy this. Control X. Oh, okay. Run this. running right here. स्ट्रॉन्ग वन है और वीक जीरो है, देन अब हम यहाँ पे आ गए, ये है आइसोलेटेड ब्लॉक। ठीक है, यहाँ से यहाँ तक आइसोलेटेड ब्लॉक है। यहाँ पे ब्रांच में दे आर parent dot borrow mute borrowing the met and downgrade for use for the weak reference. So let's say borrow strong one weak one, फिर strong two हो गया, weak zero रहा because it got out of scope. Parent none हो गया and reference count one or weak zero, and that's how it is implemented. So if you have any questions about that, you can reach out to me. Summary: this chapter covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default with regular references. The box key. Mhm. The box T has a known size and points to data allocated on the heap. The RC type keeps track of the number of references to data on the heap so that data can have multiple owners. The RefCell T type with its interior mutability gives us a type that we can use when we need an immutable type. And this is pretty much theory because we have already discussed about DREF. There are multiple major concepts that we have learned. RefCell, RC reference counted, box smart pointer, stack versus heap. We have also covered how deref and drop traits work, and what's the major concept, why the pointers are important in Rust, how it helps us in working with, let's say, strings and other stuff. So I hope you have learned a lot of stuff from this video. If you did, so you can uh, s- uh, reach out. If you have any questions, you can reach out to me through my socials, or you can comment in on the YouTube video. Uh, so I'll try to be as responsive as possible, and if needed, I'll create a separate video for that specific query. So we will cover the concurrency and then asynchronous programming. We will move on to the asynchronous programming, and then we will build multiple other major projects. Like for the asynchronous programming, we will create like backends for different things. We will use Axiom, or we will also use Tokyo runtime. So we will also cover all these stuff later on when we get onto these topics. So I hope you have learned a lot of things from this video. So see you guys in next video, and take care till then. Bye.